Alright gang, here we go. This is Physics Unit 3, Part 3. Okay, so in this unit, or this part, we're going to talk about mechanical energy and power. Okay, so mechanical energy is not a new form of energy that we didn't talk about before. Remember, we talked about kinetic energy, that was the energy of motion, and then part 2 we talked about potential energy, and that was the energy involved with holding something against the things that are acting on it around it, right? Is the idea that if you let go of something, that it's going to start having energy of its own. All right. Then we have this idea of mechanical energy, and mechanical energy is the combination of kinetic and potential energy combined. Okay, so this is how it's defined here, this formula right here, where it's the combination. Mechanical energy is just the simple addition of all the kinetic energy. Of course, my red pen isn't going to work. My kinetic energy plus the potential energy due to gravity plus potential energy of whatever elastic things are acting on it. All three of them added together. Okay, so let's do a couple ideas here. So let's say we have a 1 kilogram book, or 1.00 kilogram book, and we're dropping it from a height of 2 meters. Assume no air resistance, thank goodness. All right, and we need to calculate the potential and kinetic energy at the instant the book is released. Well, we know potential energy, so this has got to be due to gravity, right? Because there's no spring involved, and so that's equal to mgh. All right, so the mass of the book is 1.00, gravity is 9.81, and the height is 2 meters. So 2.00. Okay, so that means the potential energy due to gravity would be 1 times 2 times 9.81, or 2 times 9.81, which is like 19.62. Okay, but we'll say 19.6 joules. All right, so that's our potential energy due to gravity at before we start. Well, the kinetic energy is going to be equal to 1/2 mv squared. Well, we know that the mass of the book is 1.00, but what's the velocity? Well, the velocity hasn't changed, right? So the velocity would have to be, or the velocity, this is right as we're dropping it, so the velocity is 0, right? So that means our kinetic energy when we start is equal to 0 joules. And that makes sense, right? Because we haven't started to drop it yet, so so it hasn't started to move, right? Or it hasn't started to drop, right? So it hasn't started to move, so therefore the kinetic energy would have to be 0. That makes sense. All right, now we want to find the kinetic and potential energy when the book is falling. So let's do potential energy first. Well, the potential energy due to gravity is equal to mgh. I'm just going to skip through this here. So mass is 1.00, right? 1.00, and 9.81 for gravity. And the height, well, the height, it's fallen 1 meter. It started at 2, so it'd be 2 minus 1, or just 1. Okay, so we'll be at 9.81 joules, right? That's the potential energy due to gravity. All right, so that's got that guy here. Now the kinetic energy, now this is more exciting. We want to find kinetic energy. Well, kinetic energy is equal to 1/2 mv squared. Now let's think about this. What else do we know about kinetic energy? Well, we know that kinetic energy is equal to, let's see if this works. I just kind of thought if we could do this, it'd be a lot easier. We could use kinematic equations to find that velocity, right? Initial velocity would be 0, final velocity would be what we're trying to solve for, delta x, or delta y would be 1.0. Yeah, we could do that. Or we know from the first part here that the change in work is equal to, no, this isn't going to work. We're just going to have to do it the kinematic way. All right. Yeah. Anyway, so we're going to have to do it the kinematic way. So we know, let's see, what kind of information do we have? We have y is equal to 1.0, right? And it's falling, so it'd be a negative 1.0 meters. We know the acceleration due to gravity is equal to negative 9.81 meters per second squared. And then our initial velocity, well, we know that's 0 meters per second. And we know our final velocity is equal to, well, that's what we're trying to find, right? So that's what we got so far. So if we look at our kinematics equations, let me just pull up my list just so I don't remember it wrong on the video. Okay, so we're going to pick one of our kinematic equations here. We don't have time, so the only kinematic equation that doesn't have time in it, I'm picking up the wrong pen again. Okay, the only kinematic equation that doesn't have time is this guy. Velocity final squared is equal to velocity initial squared plus 2AD, and in this case it would be delta y. All right. So this is going to be 0. That goes to 0 because our initial velocity is 0. So that means final velocity squared is equal to 2a delta y. All right, so final velocity is equal to the square root of 2a delta y. And we can just plug in our guys here. So final velocity is equal to the square root of 2 times our acceleration, which is negative 9.81, and then our delta y, which is negative 1.0. All right. So our final velocity is equal to, all right, and we're doing all this because we need to find that velocity so we can plug it into our kinetic energy equation here. So the square root of 2 times negative 9.81 times negative 1, and we get 4.43. This would be meters per second. Now we can take that guy, we can plug it into the kinetic energy formula up here. So our kinetic energy is equal to 1/2 times the mass, which is 1.0, 0 times the velocity we just found, which is 4.43 squared, right? I'll put a line there just so it's not confusing. So we'll take that guy, square it, times 1 divided by 2, get 9.81. All right, so the kinetic energy when it's fallen for 1 meter is equal to 9.81 joules. All right. Calculate the potential. Last one, I promise. Calculate the potential and kinetic energy just as the book reaches the floor. Well, the potential energy due to gravity is equal to mgh. Well, when we just reach the floor, that means our h is equal to 0. So that's 0. So anything multiplied by 0, so that means the potential energy due to gravity is equal to 0. All right. So the potential energy is 0. Now let's think about kinetic energy. We'll skip through this because we just did all the derivation before. Kinetic energy is equal to 1/2 mv squared. Okay, and we know that the velocity final is equal to the square root of 2a delta y. Okay, and in this case our a is still the same, but our y is now the full 2 meters. So velocity final is equal to the square root of 2 times negative 9.81 times our negative 2.00. All right, so our final velocity is equal to square root of 2 times negative 9.81 times negative 2, and we get 6.26 meters per second. All right, we can take that and plug that in up here for our kinetic energy. So that's 1/2 times our mass, which is 1.00, times our velocity squared. So that would be the 6.26 squared. So that means our kinetic energy is equal to 19.62. We need only 3 sig figs, so it would be 19.6 joules. All right, so there's our kinetic energy. There's our potential energy. All right. So I went through and did all these earlier and kind of did just a couple more, plugged them into a spreadsheet so it'd be a little bit easier to run with. And so, so notice here that, remember, our mechanical energy is always equal to the potential energies plus the kinetic energies. Okay, so so I took this column here plus this column and got this value. Okay, 19.6 plus 0 is 19.6. At 1/2 meter, I got 14.7 for potential, 4.9 for the kinetic, and I got 19.6. And then 9.8, 9.8, 19.6. Are you noticing a pattern here? Okay, notice that our mechanical energy is not changing. Okay, so the total energy of our system is conserved. It's just converting itself from potential to kinetic energy. Notice that the potential energy, as we started at 0, at height of 0 up there, and then we fell 0.5, 1, 1.5, 2, our potential energy goes down because we're losing height. Our kinetic energy, though, is going to go up because we're moving faster and faster as we fall. Okay, so there's this idea of the conservation of mechanical energy, and this is a super important part for the whole next chapter. okay, collisions, and so on and so forth. So you really got to understand this, all right? Initial mechanical energy is equal to the final mechanical energy as long as you don't have any friction. So remember in our following book, we neglected air resistance. We just said, well, let's not worry about it. And notice that, and so our mechanical energy was conserved. If we had to calculate some sort of friction factor in there, and you're totally capable of doing that because last unit we talked all about friction, okay, and how to calculate how much friction is of slowing something down, so on and so forth, okay. But anyway, so mechanical energy, in the absence of friction, mechanical energy is conserved. All right, so the sum of kinetic and potential energy is going to remain constant. Okay, and we already talked about this. All right. So a couple of things that you need to make sure that you understand about conservation of mechanical energy here. All right, is that the acceleration does not have to be constant, okay? So this is a really important concept because like that means that if you're designing a roller coaster, for example, you could have a downhill and an uphill and a downhill like this, you know, as you make your roller coaster, you know that your acceleration is going to change during this whole thing, right? You're going to have a big negative acceleration as you go down, then an increase, and then a zero, and then a negative, and then a zero here, and then a negative, and then a zero, and then, you know, you're going to have a varying acceleration as you go on your roller coaster here. Okay, so, but our mechanical energy, assuming that we make a completely frictionless roller coaster, which is not possible, but anyway, if we had a completely frictionless roller coaster, our mechanical energy would be constant. It would be conserved. All right. Mechanical energy cannot be conserved if friction is present. All right. If we say friction is negligible, conservation of mechanical energy is reasonably accurate. So there are places like, so, you know, you might be thinking, well, what's even the point of this if we have to ignore, you know, friction? There are cases where friction is pretty much negligible, like ice skaters. You know, if you're sliding on ice, maglev trades essentially are, you know, especially if you do them like, Elon Musk is trying to build those underwater, or the underwater. I'm sure he's trying to do that too. So, but he's trying to build the tunnels, you know, and those are going to be either filled with, they're going to be vacuumed and then filled with just a little bit of nitrogen, is what my understanding is. And then, so those guys are essentially air. So because they're maglev, right? They're magnets keeping them apart. So there's no friction of them running across each other, and then there's no air friction or air resistance by the things because it's at such like a negative pressure. All right. Anyway, and then there's also like a pendulum as it swings back and forth, and pendulum, you know, that's where you've got like a string attached to, and then there's a ball, and this ball kind of goes that way and then that way. That's essentially frictionless. All right. But consider like something like a child going down a slide, and if that slide has friction on it, so, you know, which is normal, the mechanical energy gets lost as he slides down, right? It becomes less and less. So, you know, he's got quite a bit of potential energy. As he goes down, some of it gets, some of the potential energy converts to kinetic energy, and that's why he speeds up as he goes down the slide. But some of it also gets turned into like heat, right? So if you go down a slide with enough mechanical or with enough friction, you know, you'll feel your legs will get warm as you go down. Okay. So this lost energy turns into non-mechanical energy. So it could be nuclear, it could be chemical, or in the case of the slide, it would be thermal, right? The kid's legs will get warm as it goes down the hill. All right, let's do this. Okay, so we've got a small 10-gram ball, and it's held in a slingshot that's stretched to 6 centimeters. The spring constant is 2 times 10 squared. Okay, Newton meter. So this is essentially just 200 Newton meters. Okay, so remember that's the spring constant. That's just essentially telling us how strong that slingshot is. All right, it says, what is the elastic potential energy of the slingshot before release? Well, potential energy elastic is equal to 1/2 kx squared. All right, so we have 1/2. The k value is this guy here, our spring constant, so that's the 200, and then the x value is how much we're stretched, and so that's 6 centimeters, but remember we need it in meters because that guy's in meters, right? So it would be 0.060 meters. Okay, so we can plug all that into our calculator, so we get 200 divided by 2 times 0.060, and so we get, I probably could have done that in my head, huh? So anyway, so that's, let's see, 2 sig figs, so 6.0 joules. All right, so that's our potential energy. So we're going to assume that this is completely frictionless. So really, that's our potential energy. So everything we do is going to be related back to that 6 joules, okay? Because we're saying mechanical energy is conserved. So what is the kinetic energy of the ball right after the slingshot is released? So we let go of the slingshot, the ball starts to fly. What is the kinetic energy? Well, kinetic energy, we know kinetic energy is equal to 1/2 mv squared. But we don't have a speed here, right? So that's not going to help us very much. But we do have is how much energy, potential energy it has. And we know that the mechanical energy is conserved, so that means the potential energy here got converted to kinetic energy. All right, so that means the kinetic energy would have to be equal to 6.0 joules because it got conserved, right? All of the potential energy of the slingshot got turned into kinetic energy of the ball at that right instant, right? You let go of the slingshot, and before, ball or air resistance or anything starts acting on it, all the potential energy gets converted into kinetic energy. All right, so it's got to be 6.0 joules as well. All right, what is the ball's speed at the instant it leaves the slingshot? Well, now is where we can use the kinetic energy equals 1/2 mv squared, right? So kinetic energy equals 1/2 mv squared. Okay, so we could solve for velocity. That'll give us the speed, right? Because speed is just the magnitude of velocity. So I don't have vertical room here, so I'm going to draw this double arrow. So that means my velocity would be equal to 2 times my kinetic energy divided by mass. We got to take the square root of that. Did I do all that right? So multiply by 2 divided by m and then take the square root. All right, so it'd be the square root of 2 times our kinetic energy, which is 6, divided by the mass of our ball, which is 10 grams. But let's think about this for a second. Don't get fouled up. Remember, grams, the SI unit for grams is kilograms, right? So really, we got to move it over 3 decimals, so this would be 0.01 kilograms. All right, 0.01 kilograms. All right, so we take 12 divided by 0.01. We take the square root of that. All right, and so our ball is moving at 34. How many sig figs? Well, just 2. So it would be 35 meters per second. Okay, so 35 meters per second. Let me just make sure I got the same value I did earlier. Yeah, okay. So 35 meters per second. All right, how high does the ball rise if it is shot directly upward? Now, you could do this with kinematics, right? You could just, well, we're aiming it upwards, acceleration's down, and negative 9 point blah, 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 blah. It'd be a lot harder to do, right? But we can have a way easier to do it now. We've got a new tool in our tool belt. We know that the potential energy due to gravity is equal to mgh, okay? So really, we just want to solve for h, right? So if we do the same idea we did up here, we have potential energy, right? Potential energy due to gravity. We're assuming that this energy is conserved. So the potential energy due to gravity is going to be equal to the potential energy elastic that we started with, which would be 6.0 joules, right? So if we solve for h, well, our h is just going to be equal to the potential energy due to gravity divided by the mass times gravity, okay? So potential energy due to gravity is 6.0. The mass of the ball, remember, don't forget to convert it to kilograms, 0.01 times 9.81. All right, so we take 6 divided by 0.01 times 9.81. And we get 61, and remember 2 sig figs here still, so 61 meters. So that's how far up in the air our little slingshotted ball will go, 61 meters. All right, let's see here. All right, now we're talking about power. Now we're cooking with juice. All right, so power is and you can read this on your own. I don't really want to talk about it. So power is the measure of energy transfer, and it's a rate. So because it's a rate, that means we're going to involve time. Okay, so when we talk about power, it's kind of using this idea of work. Remember, because work was energy transfer, right? We're taking force and times distance, right? And then power is taking that work value and saying under what time did it take place, right? Because you could do the same amount of work, but it could take place like over millions of years, like an iceberg that's going across the continent very, very slowly, right? Or we could do, or it could take place very, very quickly, but like the amount of power that it would take would be vastly different, okay? That's kind of the idea of the previous slide with engines and so on and so forth. Okay, so here's the two formulas for power that you need to know. Power is equal to work divided by the time interval, okay? And remember to always use, this will be joules, and this will be seconds, all right? And then we could also say that the alternative form of this, and this formula is also pretty handy, is that it's the force of whatever you're doing times the speed, okay? Force times speed, or work over time, all right? Units are joules per second, okay? And this is also called a watt. A watt and a joule per second are equal to each other. Okay, don't get this confused. This is, I know we use capital W for work in part 1, but this is our joules per second. This is our watts. Okay, so the unit is watts. Work is something else. All right, and it's equivalent to this, or Newton times a meter. Right, same idea. Newton meter over seconds. Sorry, Newton meter times seconds over seconds. Anyway, you've probably heard of horsepowers before. Okay, horsepower is another unit of power in the avoirdupois system. But anyway, and so 1 horsepower is about equal to 746 watts. Okay, so when you talk about how many horsepowers your engine has, it's 1 horsepower is about 746 watts. All right. So light bulbs tell you how many watts it uses, right? A 100-watt bulb consumes 100 joules of energy every second, right? And so one of the big things that is being changed is using, producing more light or having more efficient light bulbs, meaning it's going to turn more of the energy they use into visible light as opposed to turning it into heat or some other form of energy. All right. Okay, so here we go. One last practice problem and we'll call it good. Okay. 2 horses pull a cart. Each exerts a force of 250 newtons at a speed of 2.0 meters per second for 10 minutes. All right, and we want to calculate the power. Well, remember, the power, we have 2 different formulas. Power is equal to watts over some change in time, but it's also equal to force times the speed, right, or velocity. Okay, now let's think about this. So we don't have work value, okay, and we don't have a time value. We could certainly find work, and we have a time value. Okay, or we could use this. We have force and we have speed. Well, that's easy. Okay, so let's think about how much force. So it says each exerts a force of 250 newtons, but there's 2 horses, right? So that means our total force is equal to 2 times 250. So there's 500 newtons of force acting on our cart. So that's 500 newtons. All right, and then the speed is 2.0. So our power would be equal to the force times the speed. All right, and the force is 500 and the speed is 2.0, so that means we have 1,000 meters per second, or sorry, 1,000 joules per second. All right, would be our units here. Now let's think about sig figs. This guy's got 2, this guy's got 4, so our answer only needs 2. So we put a line there to represent that, or it could be 1.0 times 10 to the 3rd joules per second, okay, or it'd be watts. Okay, how much work? So that's that answer right there, 1.0 times 10 to the 3rd watts. Okay, how much work is done by the 2 horses? All right, now since we have power and we have a change in time, we can use this formula here, only we're solving for work. So we know power is equal to work over the change in time. Okay, so that means work has to be equal to power times the change in time. All right, so the power is 1.0 times 10 to the 3rd. All right, and our change in time is 10 minutes. But remember, this is in joules per seconds, so we got to convert this. So we'll do a little bit of dimensional analysis. We'll put minutes in the bottom. We'll put it seconds up top. There are 60 seconds for every 1 minute, so that means it's 600 seconds. Okay, so the delta time, change in time would be 600 seconds. All right, so this guy would be 1.0 times 10, so that would be 6 with 5 zeros after it. 600,000 joules because it's watts. So if we put this in scientific notation, it would become 6, and we need 2 sig figs, so 6.0 times 10 to the 5th joules. All right. and then 1.3 times 10 to the third joules per second. And that's what I got earlier today, so that's a good thing. All right, so anyway, so that's the end of part 3. We talked about mechanical energy, conservation of mechanical energy, and we talked about power. Make sure you do those practice problems. Come see me if you have any questions, and I'll see you on the flip side.